Hello, in this video we're going to be talking about continuity over an interval and dealing with removable discontinuities. Now, quick reminder about continuity, we need to make sure that the limit as the function approaches a particular value is the same value that the function actually reaches. You still got to do that left-right check. Continuity on an interval, it could just be on an open interval, like a set of numbers on that function. You could also have a continuous function. A continuous function is where it's always working. We just never have any problems with continuity across the entire function. If we have a single point where the function is not continuous, then it would not be a continuous function. It can still be a function, just wouldn't be a continuous function. In these examples, we want to figure out where the function is not continuous. So there's an obvious spot right here where we've got the hole in the graph, and we've got this spot right here where the function doesn't even have a limit. Now you can see it in the equation too, because in the first one, you could factor out an x, and when you factor out that x, that would cancel with the x in the numerator. So we would have that removable discontinuity because it cancels out, and it can be sort of like in some ways removed from the equation. We don't have we have a non-removable discontinuity at x equals 1 because we don't even have a limit. Over on this one, we can see that on the graph, the function is continuous, that it is totally connected at all points. You can see it in the equation because I can't factor that denominator, so it won't cancel with the x. And there's no value I could put into x squared plus 1 in the real number line. That would make our function have a 0 in the denominator. So f is continuous on all real values. We see a similar situation down here as we did up here. So this is a removable discontinuity at -2. However, the x minus 5 that we would get in the denominator, that doesn't cancel with the numerator and thus creates a non-removable discontinuity. So right now we can see that if we put in an x minus 3, that is going to cause a discontinuity since you can't divide by 0. So what you can do is you can factor that numerator and get that denominator to cancel itself out. So that x plus 3 and x plus 3 cancel, and you're left with just y equals x minus 3. Something to note in general when you're trying to determine if a function is continuous is if you have a polynomial function, all polynomial functions are continuous on their entire interval. Write that down. So if you're ever given a problem and you're trying to determine continuity, you can just say, hey, it's a polynomial, so we are definitely continuous. Couple more examples to look at. Again, as we see this one, we're trying to say, oh, well, based on the graph, yeah, that's definitely not a removable discontinuity because our limit doesn't even exist. You could also say, hey, is there a way that I would be able to cancel this x plus 7 with the x plus 7 and an absolute value? No, there's not. So that is a non-removable discontinuity at x equals -7. Now, this piecewise function is interesting because there are a few things that we need to consider before we can say that this thing is continuous. We need to make sure that the left and the right hand limits are matching up, so we have a good limit, and we want to make sure that they're reaching the same point. This just straight x, as it's approaching 1, on the x-axis, it is approaching y on the x-axis. Same thing with an x squared. As we come in from the right-hand side, approaching 1 on the x-axis, we are approaching 1 on the y-axis. So the limit is matching up. Our limit does exist. Then we need to make sure, hey, when they get there, is that same value true? Yes. 1, if we put that in there, that's a 1. If we put a 1 into x squared, that's a 1 squared, that's a 1. So this one is continuous because we just need to check that single point. X is a polynomial, it's continuous. X squared is a polynomial, it's continuous. We just have to check that spot where the two are meeting up. Let's use these ideas that we've been doing in order to figure out how we can make this function behave itself and be a continuous function. So looking at it, we want to figure out some value of a so that it is a continuous function. What are we going to put in there? Now, I'm looking at that numerator and I say to myself, hey, I could try to do that canceling stuff. I can make that an x plus a and then an x minus a over x minus a. That would cancel with each other, and I would just have that x plus a. And that would be just this top part. Now, the idea is we want these two things to head towards the same thing. So we want to make sure that purple part matches up with this spot down here. So that's just saying, well, x plus a is going to equal 8. So now we're right on the road of having an equation that we can actually solve. However, this equation has too many variables in it. It has x and a, and all I want to figure out is a. So I need a little bit more information. Fortunately, the problem gave me something. It told me that, hey, by the way, we want x to equal a. Like that was technically part of the thing that they were setting up in order for us to make this continuous function. Piecewise function. Mel's distracting me. But then we can replace that x with an a. So now we've got a plus a equals 8. And a little simple solve later, we get a equaling 4. And we would check that to make sure that our limit is approaching that same thing. Is that numerator, is the limit as x approaches 4, is that heading towards 8? So if we plug in our a, we get x squared minus 16 over x minus 4. And if we were to do our same sort of like factor and cancel like we did over here, we get x plus 4. That's not the actual function, but it's how our limit is going to behave. And we can see as x is approaching 4, we are going to be approaching 8, which is the green part on the bottom. So everything is checking out A-OK. Mel, you're not being helpful, okay? Another problem similar to the last, this one we're going to just start by thinking about our limits instead of trying to make the two things match up. Because why not? The first limit is 4 sine x over just x. I want to try to figure out where that limit is going to be so I can make sure that the two limits match up. Sine x over x, that's one of their goofy limits. So I want to try to break this thing up a little bit so that I can do the limit. So I'm going to pull the 4 in front. So I got the limit as x approaches 0, because the limit of 4 is just going to be 4. But then we've got the limit of sine x over x, which we know to be just 1. So that's the same as 4 times 1. So our top limit is 4. So we want to make sure that the bottom limit also ends up being 4. Because if those two limits match up and we make sure that they both equal the same thing at that point, then we'll have a continuous function. So on the bottom, that one you can just direct substitute. So you get a minus 2 times 0, which is just, well, a. So we want those two things to match up. So, well, hey, guess what? We should just make our a equal to 4. Hey, two problems and two answers of 4. You can check that up above by making sure that we just did our top limit, because as it's approaching 0, we're heading towards 4. And if you plug that into the bottom, you get 4 minus 2 times 0. Oh, that's also 4. So the two things should be matching up. And that concludes everything for our continuity on an interval. A reminder about continuity is that you need to make sure the limit of where the function is going is where it actually ends up. Also, reminder that if you ever have a polynomial function, you're trying to determine if it's continuous, don't worry about it. All polynomial functions are continuous. And finally, don't forget, you're always checking those limits to make sure that the left and the right hand limits are heading towards that same thing. That's how you make sure you've got that good limit. Thanks for watching. Bye-bye.